Good morning, ladies and gentlemen. I'd like to welcome you to this joint webinar hosted by EU-SysFlex and OSMOSE. Both are EU-funded innovation and research projects under Horizon 2020, and both commenced in 2017 and are well on their way to completion. And given that this webinar is happening today, we're at a very interesting point in the projects as they're very advanced, with lots of interesting results, which have the potential to be very impactful with respect to addressing system operation challenges, with the respect to integration of high volumes of variable resi in Europe. And the fact that both projects are looking at the challenges in different ways and coming at it from different angles creates the opportunity to have a very interesting and thought-provoking webinar, which I'm delighted to moderate. This is the first part of a series of 3 webinars that we're holding this week. And we do hope that you might be able to join us at our subsequent webinars, which I'm sure will be of great interest also. So the title of this webinar is High-Res Scenarios, from Adequacy to Stability Challenges and New Solutions. And in this webinar, the OSMOSE and EU-SysFlex projects will present the scenarios they've considered and the key challenges identified. First, OSMOSE will present its new method to define cost-effective mix of flexibility and preliminary results. And the EU-SysFlex will complete this vision by highlighting the long-term scarcities on adequacy and the frequency stability in their own scenarios. And then finally, the 2 projects will present demonstration projects providing new frequency and stability services. We've 3 very interesting topics on our agenda this morning, and equally 3 very interesting, or a set of speakers to cover those 3 topics. Marianne Evans of EDF, who's the Technical Director of EU-SysFlex, and Nathalie Grisey of RTE, who's the Coordinator of OSMOSE, will introduce their projects. And then we will have 3 topics, the first on the long-term scenarios and adequacy challenges. OSMOSE will be represented here by Jans Wippensan, and EU-SysFlex scenarios will be covered by Caroline Bono, if she has joined us now. I know she had difficulty getting online, but we will have that topic covered. The second topic is frequency and stability challenges, and that will be covered by Sheila Nolan, my colleague from EirGrid for EU-SysFlex, on the analysis of scarcities. And Carmen Cardozo from RTE will cover grid forming to ensure stability on behalf of OSMOSE. And then the third topic is demonstration of the new flexibility provider. So this is our demonstration projects. So EU-SysFlex will be presented by Miguel Marquez, who will talk about our VPP and the provision of FCR from wind farms. And OSMOSE will be represented by Alessio Severo from Terna and the provision of frequency and voltage regulation by wind farms. And finally, then we'll have a Q&A session. So my name, apologies, I should have said at the start, is John Lowry from EirGrid, the Transmission System Operator of Ireland, and I will be your moderator this morning. So I'm going to now hand you over to Marianne for her presentation. But just before that, I just want to maybe talk a little bit about questions. So what we're going to do here is please use the Q&A section and specify the target speaker. There will be a brief Q&A session after each presentation so that the questions are live in your head, but we'll have to keep that tight. So try and keep your questions to the end also. And in some cases, if questions aren't answered during the Q&A session, then we will follow up by email. That's our intention on you. So I'll hand over to Marianne.
Good morning, everyone. So I'm Marianne Evans. Thank you, John, for the introduction. And I will very briefly introduce our projects. So next slide, please, with the facts and figures of the projects. You can see that it's answering the same call as the OSMOSE projects. It's a huge demonstration project with a total budget over 26 million euros. It started in November 2017, and it will go on until a little bit more than October, because we have an extension after the COVID, so February 2022. We have a large consortium that you can see here on the right of the slide, with 34 organizations with players from the whole power system, European power system, many TSOs, many DSOs as well, aggregators, technology providers, consultants, and of course, research institutes and universities. And you can see the list here on the right with the demonstration and studies from all over, coming from partners all over Europe. Next slide, please. So the goal of the EU-SysFlex project is to demonstrate reliable and efficient flexibility solutions so that we can reach the energy transition targets of the European policies, which are to integrate over 50% renewable energy sources in the European power system. As you can see here on the figure, we're trying to materialize the increase in system complexity when we're going from a scale of 30% res, which is more or less the case today, to a target over 50% res in 2030, and more, of course, in the following years. So the mix is changing with a greater reliance on variable sources of electricity, but also on the demand sides, there are some changes with electrification of heat, of cooling, and of course, electric mobility as well. And we are also integrating a deployment of battery storage as well to deal with the variability of the sources. The system structure is changing as well, because as we are moving towards these sources of electricity, we're moving from a very centralized system to an increasing decentralized system with many and smaller sources. So next slide, please. This led us in the next slide, please. Yeah, so this led us to the first steps in the project, and we're carrying on working on the scenarios all through the project to build scenarios to describe this future power system and how it is changing, how the mix is changing. So as you can see from the figures here, we built two core scenarios that will be detailed a bit further in the presentation, the first section of the presentation, from energy transition with a share of 52% res, and renewable ambition with an even higher share of res, 66%, sorry, of electrical renewable energy sources in 2030. But what we focused on is not only the res targets, but the variable res targets, because variable res, mainly wind and PV and solar power, are also non-synchronous. And this is what will interest us and what we will analyze in the second section afterwards, which is the impact of the share of non-synchronous in the system. So as you can see here, our core scenarios worked on 23 and 35% share of variable res. And this translates, as you can see on the figure on the right-hand side of the slides, with share of instantaneous non-synchronous penetration that can reach, so you can see for several countries here illustrated. For example, for Spain, you have a mean value, mean share of non-synchronous of 73%, but it leads to hours in the system where the share of non-synchronous reaches 95%. And even for countries where the mean value of non-synchronous of variable is a bit lower, is under 40% for France, for example, we have some hours where the share of non-synchronous reaches 85%. So high-res scenarios, and you will see then how it how it leads to challenges, but high-res scenarios translate in increasing levels of variable res and challengingly high shares of non-synchronous penetration in the systems. Next slide, please. And the shift to these variable, non-synchronous and decentralized res creates key technical challenges for the system, and they will be, so here on the figure we represented some of the main challenges that we worked on, which are the stability challenges, but also we are identified, so we worked on the stability issues, and Sheila Nolan will detail this work. We also analyzed scarcities in the system appearing in adequacy, but also in congestion management and in system operation and restoration. Just so that you know, here we have short presentation, but there is a webinar of 2 hours from the EU-SysFlex detailing all the results that you can find on the website. Final slide, I think, please. So, so just before we thank you and give us the detail, if you want to see the detailed presentation on the website, we will finally, so we're working now on also mitigation actions and solution to these scarcities. It's work in progress. We have a first set of analysis that is just coming out this month, and Miguel will present also some of the solutions that are tested to mitigate the scarcities that I've just introduced in the demonstration of the EU-SysFlex projects. So have a nice webinar, and thank you very much.
Thank you very much, Marianne. Very interesting opening. I hope that gives people a flavor of, or an overview of EU-SysFlex. We'll move on now to Nathalie, who'll present an introduction to the OSMOSE project. We received our first question as well. So it's a light one. It's always good for an opening question about respect to the slides. Are we going to share the slides? I think, and I believe that the intent is to share the slides on our collective website. So yes, you will have access to the slides, and it may even be a link to it may even be shared. But maybe you'll have access to them. So I'll hand over to Nathalie.
Thank you, John. So good morning, everyone. So I'm Nathalie Grisey from RT, the French TSO, and I'm the OSMOSE coordinator. So it's a very great pleasure for us to organize this series of webinar with EU-SysFlex. So thank you, EU-SysFlex and John and Marianne, and then all the speakers, of course. So next slide, please. So OSMOSE is a project about flexibility. So there are many definitions of flexibility. Ours in the project is that it's the power system's ability to cope with variability and uncertainty in demand, generation, and grid over different time scales. It means that in the project, we think that flexibility is not only in the short term, a short-term issue, but actually there are relations between the short-term issues and also the long-term issues. And so obviously, as said by Marianne previously, the power system is evolving, and then comes new flexibility needs related to the penetration of renewables and also to the modification of the electrical demand. But fortunately, we also have new sources of flexibility like storage, like the demand, like renewables, and also like the flexibility of the grid. And thus in the project, we work on how those new sources can address the new needs of flexibility. Next slide, please. So the OSMOSE consortium, so like EU-SysFlex, we are an EU-funded project with a budget of 27 million euros, 33 partners from 9 countries. So we have TSOs, we have industrials, we have academics partners, as you can see on the slides, the work package leaders, so RT as the coordinator, also Red Electrica, Terna, and LS, which are the TSO from Spain, Italy, and Slovenia. And we also have CEA and TU Berlin as web package leaders. We started in 2018 and we will end next April. So we are entering our final year. Thank you. So the content of our project. So first, on one hand of the project, we are doing simulations of long-term scenarios in order to identify future needs and sources of flexibility, and also in the meantime to develop new tools and methods for flexibility assessments. So we have two work packages dealing with that. And on the other end of the project, we have 4 demonstrators. Each one is led by a transmission system operator. And so the demonstrators want to foster the participation of new flexibility providers and to demonstrate new flexibility services and also multi-services capabilities. And then we also have a work packages which is dealing with scaling up and replication. So today, next slide, please. Yes, thank you. No, previous one, thank you. So today you have 3 presentations. So one about our work package 1, which is called Optimal Mix of Flexibilities. And then you will have 2 presentations from 2 of our 4 demos. One, which is the demo called Grid Farming by Multi-Services Hybrid Storage, which will be presented by Ken. And then we'll have a presentation from our Italian demo, which is called Multi-Services by Coordinated Grid Devices, Large Demand Response, and REST. So as for EU-SysFlex, if you want to know more on our project, of course, you can go to our website. And so I can leave the floor to the next speakers.
Thank you, Nathalie. Maybe we just have a very brief question and discussion to Nathalie and Marianne, and obviously there's a lot of similarities in terms of the approach of the projects and addressing similar challenges. Just maybe if you would like to just highlight what you see as being the key differentiators between the 2 projects, and what you see as being, the ultimate goal and the ultimate learnings, and who needs to sit up and listen about your project. So Nathalie, maybe you first.
Yes. So for sure, we have a lot of similarities, but I think at the end, to reach our target to decarbonize the system, we need a lot of different solutions. And basically, in OSMOSE and EU-SysFlex, we consider different ones. As you will see later on the presentation, for example, our demos are very different. I think EU-SysFlex, you have more demos led by distribution system operators, whereas we don't have this kind of demo in OSMOSE. So I cannot go into the details of detailing everything, but I think in the presentations coming, you will see that basically they are very complementary, the two projects.
Marianne?
Yes, I completely agree with what Nathalie was saying. Maybe I will add also in the simulations, EU-SysFlex, what maybe we didn't have full detail grid for all systems, but we did a lot of simulation as well to see the impact on voltage control, and I think this is an interesting area that not only frequency or inertia challenges, but also challenges in voltage and other issues. And I think here we have complementary views as well, not only on the solutions, but on the type of analysis that were led in the 2 projects.
Very good, very good. Okay, so very complementary, I would suggest. So we'll move on now to our first topic, and I'm going to introduce you to Jens, who is representing the OSMOSE project on the optimal mix of flexibilities.
Yeah, thank you, John. So the first topic is going to be about, as Nathalie mentioned, the first work package of OSMOSE. And the research question here was basically how the long-term development of the power sector would look like in terms of the energy transition in Europe, and what the impact then on the power sector would be. And we basically wanted to know what kind of flexibility demands there will be in a future system and how they could be met. And so first of all, we basically looked at the big picture here with an energy system model, and then we linked this with more detailed power sector model. And for the scenarios, this basically is less a focus on the technical details of the grid operation, so for example, inertia, reactive power, and so on, but more on a future structure of supply and demand, because it's very long-term. This doesn't mean that obviously also the short-term questions are being answered here in this work package and the project overall. Just want to focus on the long-term and bigger picture today. So what are flexibilities? Obviously, there are different kinds of flexibilities, but in general, we use the definition that it's the power system's ability to cope with variability and uncertainty in demand and generation. And as you can see here, the time scale would be from short-term flexibility demand that stems from forecast errors via medium-term about the forecasts themselves, and the long-term flexibility, which are more the fundamentals of the system. And in this case, it's less about the reaction time, but more about the actual energy quantities. And this is what we want to focus on here in the scenarios that we're looking at in the OSMOSE project. And in general, you can state that if we increase the share of variable renewables, then we also increase the need for flexibilities. And at the same time, we can see that the electrification of the heat and the mobility sectors also provide new sources of flexibility that haven't been in the system up to now, or at least not in the scale that they will be in the future. So what we did was applying a model coupling between two models. So as input assumptions from the scenario definitions, as exogenous definitions, we looked at yearly emission limits. For the different scenarios, we looked at final demand for heat, mobility, and electricity. And we obviously had a lot of technology and cost data for the renewables, for the conventional technologies, and other sources of flexibility like storages and so on. So these were input assumptions that we need to come up with in the first step. And then we fed them into our energy system model, which is called Genesis Mod. And Genesis Mod works in 5-year time steps and calculates cost-efficient pathways up to the year 2050 in our case. And the outcome here would then be the capacities and consumptions of, for example, CHP, heat pumps, electric boilers, but also electric mobility, methanization, and electrolysis. And we have some remaining potential for emissions and biomass that are not used in the Genesis mod that can then be used in the subsequent model, which is Dun-L-Mod. And Dun-L-Mod then calculates, again, cost-efficient pathways to 2050 now in 10-year time steps and for the power system alone. And in the end, we then come up with capacities, generation, and transmission in these different time steps and in the different types of scenarios that we have defined. So this is the methodology that we used in the first iteration of our scenarios, which has been done at the beginning of the project. And the spatial resolution of the two models was a little bit different. So the Genesis mod works in the regions that you can see here, and Dun-L mod works in clusters. And in these clusters, we have actually used the clusters defined in a previous e-highways project. So we are working here with the 99 e-highways clusters from the previous project. Now, looking at the different scenario assumptions, as I had mentioned, we decided to mostly base the differences in the scenarios on the emissions levels that we allow for in 2030 and 2050, but also the final energy demand. And there's also an assumption on technologies, in this case, coal. The three scenarios that we have defined is basically the middle ground, which is current goals. So this includes the current goals that are set on the European level. So that meant back then 40% emission reduction until 2030 and 80% until 2050. And you can already see that this is kind of outdated. We are currently in the process of going towards a more stricter scenario here for the European level. We also have the scenario neglected climate action, where we basically looked at the case when we will miss the 2030 and 2050 targets by 5 or 10% respectively. So that means we end up at 35% in 2030 and 70% in 2050. And on the other hand, we have the accelerated transformation scenario, where we looked at more ambitious goals, meaning 55% reduction in 2030 and 98% in 2050. And this is obviously now more where towards Europe is heading currently, which means that it's time to actually reiterate on these scenarios. And I will come to that at the end, that we're actually doing this. Looking at the final energy demand, there is also a difference here in terms of how the final demand would look like. So in neglected climate action, there's only a slight overall increase. In current goals, we have a constant final demand for electricity at high temperature heat, but there is a demand increase for low temperature heat of 20%. And then for accelerated transformation, there are moderate efficiency gains, but also the demand for low temperature heat would decrease by 25%. So we do have some efficiency measures here. And in terms of technologies, we looked at different scenarios for the coal phase out. So in the accelerated one, it's until 2035, and in the neglected climate action, we're looking at 2045. So there's a difference here between 5 years in each of these scenarios. As outcome, we have these nice Sankey diagrams. You will notice that they are kind of reverse because we're looking at the demand on the left-hand side and the sources on the right-hand side, including the different steps in between of conversion. So this is the outcome that you would get for each one of these scenarios for 2030 and for 2050. And here you can see the case for 2030 for our accelerated transformation scenario. If we look at final electricity demand, we can see that there is a slight difference here. Looking at the accelerated transformation scenario in 2030, we do have a higher final electricity demand than in the two other scenarios. And when looking at 2050, they are more or less equal, but the sources of where does final electricity demand is coming from looks a little bit different here. Yeah? So you can see that there's, for example, an increased demand for heat pumps in the accelerated transformation scenario. In current goals, there is power to X. So rising levels of electrification and gains in efficiency kind of offset each other here in these scenarios. Looking at the demand profiles for Germany, and this is now the case for accelerated transformation, we can see that if we increasingly electrify the different sectors, then there's also a great increase in the volatility of load. So the blue one would be the 2020 time series here, and the red one, the 2050 time series for the whole year. And we can obviously see that there is increased volatility in short and long term. Now, looking at the installed flexibility technologies, we can also see a major difference here, mostly between neglected climate action and then the other two scenarios, current goals achieved and accelerated transformation, which have a way higher installed capacity of our flexibility technologies. And we can see here that in both scenarios, we haven't heavily relied on, for example, lithium-ion batteries, but also electrolysis and methanation. And we can see that this demand for installed capacity even grows if we go for the accelerated transformation scenario. And there's actually a significant difference here between these two. In a second step, there was also a simulation done in Monte Carlo, simulation with an hourly dispatch using the anti-res model. And here, this is an example for the scenario current goals for 2050. And we can see that the mix then mainly is based on wind generation. So on the left-hand side, you can see a daily dispatch over a whole year for Europe. And there is still some spillage remaining in summer, also a little bit in winter. But we can basically see that all sources of flexibility are then utilized. And there is a significant power to gas usage in winter and, a gas to power usage in winter and a power to gas usage, especially in summer. And if we look a little bit more into the detail here, on the right-hand side for 2 specific weeks, actually the picture shows a couple more days than 1 week, but just zoom in on the left picture, we can see that, for example, here in the summer week, there is a nice interplay of these flexibility levers that we have. So you can see number 1 and 2, there's basically a daily cycle where batteries and PSP are used. And then we can use power to gas outside of the sunny hours. So it's a little bit more of a seasonal storage. And we can see that there is an increased power to gas generation here, in this case with clean gas, obviously, without additional capacity. So as the key takeaways from these scenario generations and the first more detailed calculations that we did, we can obviously see that, as already mentioned, electrification does greatly affect the temporal structure of our overall electricity demand. And the electrification and sector integration requires short-term flexibility, but especially the sector integration can also provide new sources of flexibility. And especially chemical storages and long-term flexibility are very important if we go further towards the deep decarbonization scenarios of the reduction of 98% until 2050.
Okay.
The work is still ongoing. It was mentioned the project is now entering the final year, and we have noted when doing the first iteration of the scenarios that there are some needed improvements and refinements for our scenario methodology. So we have this sequential coupling of two models, the energy system model and then the power sector model, which doesn't allow for very nice interplay of the flexibilities between the sectors. And this is why we have decided to refine this whole methodology by introducing a new type of model, which is called AnyMod. And this allows for a full interaction of the sectors. So we can then account for this flexibility between the sectors. And we also have a better temporal resolution, up to an hourly resolution here, actually. And we can also include gas grids and emerging hydro grids that might be there in the future. There is also an ongoing simulation in Antares, and there is basically here ongoing the use of new time series, more time series, and also more accurate geographical correlations in these time series. So in these Monte Carlo simulations, that's basically based on better data for the weather part. There's also a generation and analysis of relevant variance happening, and closer look on EV penetration and sector coupling assumptions connected to this, but also additional ones.
Yeah, Jens, we just need to move on there now. If you can wrap
yes,
it up.
just one last word. So as I mentioned in the very beginning, that we looked at the bigger picture here and more the long-term flexibilities, but the project or the work package also looked at short-term flexibilities. So just to mention this here on the right-hand side, there will be more outcome also for looking at the sizing and siting of flexibility options, reserves, and also then in terms of stability for different examples. So okay. Thank you very much, and open for questions.
Thank you very much, Jens, for that very interesting question. We are slightly behind time, so I'm going to move directly to Caroline Bono's presentation on EU-SysFlex scenarios. I know Caroline had difficulty getting online, so I'm not sure if she is with us now. Caroline?
Yes, I'm here. Good morning, everyone.
Excellent. Just in time. Excellent.
Yes.
Okay, can I just also remind everybody, all the attendees, to use the question and answer function in Zoom. It's just if you have questions as the speakers are going through their presentation, we have a record of them here, and it'll help create a little bit of discussion at the end. So please do post your questions on the question and answer function. Caroline, I'll hand over to you.
All right, so I'm going to talk about the scenarios that we use in the EU-SysFlex project. And next slide, please. I'm going to start with explaining why we build scenarios for the EU-SysFlex project. So the goal of the EU-SysFlex project is to identify issues and solutions that are associated with integrating large-scale renewable energies into the power system. So we wanted to project ourselves in scenarios with large amount of Res-E. And so we developed scenarios where we could identify some of the technical scarcities that could be associated with future European systems with large amount of renewables. And we also wanted to have scenarios to allow us to test technical and market solutions to address the scarcities. And so in the project, we wanted to have scenarios that would be shared so that we could work off of a common basis. So on the next slide, I'm going to explain how we pick the scenarios that we used. So we looked at different scenarios during a literature review, and then we defined criteria. So we wanted to have scenarios that would be consistent with the goals of the EU-SysFlex project. We wanted to have at least 50% Res-E. We wanted the scenarios to be public and also to have a breakdown by country. We wanted to have the scenarios with that incorporate the targets and policies of the European Union. They need to be recent, and we wanted to have consistent scenario years, so we could have 2 core scenarios that we could use to the project. And then we wanted to develop different geographical perimeters that would be consistent with each other. So we have a scenario that is for Europe, and then we also have scenarios for Ireland and Northern Ireland, for Central Europe, and for Scandinavia. So we use the same common basis, and then we put it in different geographical parameters to use the know-how and the strength of each of the partners. And so those are our core scenarios. And then because we want to be able to go a little bit further, we developed also network sensitivities where we are exploring different configurations and also different solutions. So for example, we challenged with using higher res. We also looked at scenarios where the res were distributed. And then we looked at flexibility solution as well as different types of interconnection to look at what the impact could be. So next slide, please. So here I'm going to talk about the scenarios that we use. So we chose the EU reference scenarios, and we used 2 different time horizons, 2030 and 2050. And for 2030, we call it energy transition in EU-SysFlex, and the 2050 horizon is called renewable ambition. And so for energy transition, we have 52% RESI in Europe. And for renewable ambition, we'll have 66% RESI. And where we expect the scarcities to appear is when we have a lot of variable res. And so on the right, you can see the map where you see the countries with the share of variable res in the production. And what you can see is that we have very high levels of variable res share inside the production. It goes up to 70%. And also what you can see is that some countries that had a lot of resi, for example, Scandinavia, has a lot less variable res. So what we see on the 2 maps is that we have scenarios with a lot of res, and we also have scenarios where we have a significant amount of variable res, so that we can actually look at the technical scarcities and also look at what solutions we could use. So on the next slide, please. I'm going to talk a little bit about the context of the EU-SysFlex scenarios. So they are built on the EU reference scenarios, and those scenarios are setting a trajectory that's based on the European policy framework. So where the 2020 renewable targets are met. It also includes some CO2 reduction targets for the different projected years, and it also includes some energy efficiency directives. And so it will also, for the different production units, will follow also will follow also like the coal phase out. And as far as the electricity demand is concerned, the electricity demand tends to increase because there's a population growth, and also there's a shift toward electricity, in particular with heating and cooling. We also have an electrification of transport for EVs as well as for rail. And we also see digital products in residential and tertiary sectors. So next slide, please. So now I'm going to speak a little bit about how we built the data set. So we based ourselves on the EU reference scenarios, where what we had for each country was the yearly production. We also have the installed capacity by fuel and the yearly demand. We also used some data from the ENSOE, the TYNDP, to get countries such as Norway and Switzerland, and also the interconnections. And from there, we actually built this big data set where we have about 6,000 files for each energy transition and renewable ambition. Our data set is has hourly data. It has also for each country, so we have the plants. We have production constraints on the plants. For example, minimal time where the plant is running. Between the countries, we have interconnections. And something that's particularly important in future scenarios where we have very high shares of renewables is that we have a lot of climatic years. And so those climate years allow us to test different climate conditions. For example, years where we have more wind or more sun, we have cold spells, we have heat waves. And so this allows us to look at different situations and to be sure that the results that we have are resilient as far as the climate is concerned. And so next slide, please. So to conclude, we use the reference scenarios for Europe that are incorporating targets, policies, and directives of the European Union. We develop scenarios and sensitivities for 4 geographical areas, so Europe, Ireland and Northern Ireland, Central Europe, and Scandinavia. And the scenarios were used throughout the EU-SysFlex project, so we could explore challenges to the future European power system, and also technical and market solutions that could address those technical scarcities and improve the resilience of the future European systems. And in the future presentation, for the presentation, you will see some of the examples and results that we have with those scenarios. Thank you very much.
Thank you very much, Karen. That was very interesting. 2 very interesting presentations setting the scene in terms of, you know, the scenarios, and one thing that's constant is change. And ever increasing challenging targets as we move towards 2030 and to net zero. Just as an open question, I suppose, to both of you, what you see as being the next iteration of scenarios analysis, and what was the biggest challenge in the piece of work that you've actually concluded to date? So I might direct that to Caroline firstly.
The biggest challenge in realizing or building the scenarios was getting all of the data to match the reference scenarios.
I would actually agree.
Yeah.
There was a similar challenge for us. There's a lot of data need, and when doing these scenarios in the way that we did it, then we have to make sure that also the outcome matches the different zones or regions we're looking at. And this is actually something that we're currently looking at in our iteration here, that we're trying to, or we did that already, match it with resources from all our partners or European partners on the project to make sure that there's consistency also on a regional level. And this will further improve the scenarios. So we will have an update of this very soon.
Okay, very good. Thank you very much for that. We'll move on now to our next topic, which is frequency and stability challenges. We'll hear from Sheila Nolan of EirGrid, representing EU-SysFlex firstly. So I'll hand over to Sheila.
Thanks, John. So today I'll speak very briefly about some of the key results from EU-SysFlex, namely the technical scarcities that were identified at high levels of renewables. And just to point out, in EU-SysFlex, we define scarcities as shortages of some technical capability that the power system would have traditionally had in good supply. And I'll describe some of these scarcities shortly. So the title of Work Package 2 in EU-SysFlex, where this technical shortfall analysis took place, is the development of new approaches for system operation with high RESI. And again, for a bit of clarity, and just to complement what Caroline has said earlier, in EU-SysFlex, we consider RESI, high RESI, to be any value of RESI that's greater than 50% on a pan-European basis. And again, as Caroline mentioned, in some of the scenarios that we look at, some countries or some systems will have much higher levels of RESI, while some countries will have much lower levels of RESI. In this project, we're also very interested in levels of non-synchronous renewable generation like wind and solar generation, which Marianne has already mentioned. So I'm going to give a very high-level overview of some of the key results to two of the questions that we're trying to answer in Work Package 2. The first question is, what are the technical scarcities of the future power system? And the second is, what solutions could we use? What solutions could we use to address those technical scarcities? So the work in EU-SysFlex on determining the technical scarcities builds upon work that took place previously in Work Package 2. Task 2.1 performed some scoping work, which reviewed the literature and categorized the scarcities that could appear at high levels of non-synchronous renewables. And this review informed the work that took place in Task 2.4 by indicating what scarcities we should be looking for. In Task 2.2, which is what Caroline was discussing, the scenarios and network sensitivities were developed. And these scenarios, and particularly the sensitivities, indicated what systems we should be investigating in order to understand the technical scarcities. Task 2.3 is where the models were developed and other bespoke tools were created. And a considerable number of models had to be developed and initialized due to the vast range of technical scarcities that we were going to be studying. And then this work from Task 2.3 informed the type of analysis that we needed to undertake. The breadth and depth of the analysis that we undertook in Task 2.4 was quite considerable. Most studies in the literature will focus on one or two scarcities at power system level, or perhaps a few different scarcities, but on a test system. And yet here we endeavored to examine multiple different scarcities across multiple different power systems. The analysis involved full year-long simulations, as well as chosen snapshots and very specific cases. Different stimuli or system disturbances were used to carry out the analysis. And a range of different metrics and indices were determined in order to understand the scale of the scarcities. So on the next slide, I've just presented a small sample of some of the results from our analysis, just to give a flavor of the work that was conducted. So EDF completed analysis for the continental European power system and found an inertia scarcity, which can cause very high rock-offs or rate of change of frequencies, in some cases greater than 2 Hz per second, which is an indication of an issue with frequency instability. Furthermore, there were many instances where the frequency nadir, which is the lowest level the frequency reaches following a system disturbance, approached load shedding levels, which we definitely want to avoid. It was also found that system split events were becoming more of a threatening issue due to increasing rate of change of frequency values, particularly in cases where the Iberian Peninsula splits from the rest of the European power system. On the next slide, I've introduced some of the work that was conducted by Ergud and Sony for the frequency analysis of the Ireland and Northern Ireland power system. It was found that without significant mitigations, there will be significant inertia scarcities in 2030, and therefore challenges associated with high rates of change of frequency. In some cases, the rates of change of frequency were so high that they needed to be limited in the actual generation dispatch themselves in order to create credible dispatches for future analysis. And this particular mitigation is an option that we also explored as a solution in further studies. It was also found for the Ireland and Northern Ireland power system that there were situations where there were very low levels of fast reserve services available. And this caused a distinct downward trend in frequency nadirs following a system disturbance. And this indicates the real importance of fast frequency response in the future. On the next slide, PSE conducted analysis of the Polish network, or sub-network of the continental power system, and identified significant scarcities in reactive power, with both under and over voltage issues being a concern as a result of the increasing levels of renewable generation, in this case, especially wind generation. What is interesting about this particular piece of analysis is the actual renewable levels, or the actual non-synchronous renewable levels in Poland in our scenarios for 2030 were actually quite low, and yet we were still seeing significant issues appearing in terms of reactive power scarcities. A lot of other scarcities were also identified, and the details can be found in our report, which is available on our website, as well as in the accompanying webinar recording, which again is available on our website. On the next slide, the conclusions from the work on the technical scarcity analysis from work package 2 is that if mitigations are not put in place by 2030, the Ireland and Northern Ireland power system will be experiencing significant technical issues in a range of different areas due to high levels of renewable generation, while the continental system will likely experience some significant scarcities as well as growing areas of concern. The Nordic power system generally appears to be evolving towards these scarcities, and these results are indicated in this table, both in terms of the increasing number of issues, but also the severity of the issues. So as you move from left to right across this table, the level of non-synchronous generation or variable renewables, as Caroline mentioned, is increasing. And as you can see, there's an increasing number of scarcities and an increasing severity of the scarcity appearing. It's important to note here that while there was no dynamic voltage scarcity identified in the continental system, there is a caveat with this. So the analysis on dynamic voltage scarcity for continental Europe only considered the Polish system, which, as I mentioned, didn't have very high levels of non-synchronous generation in our scenarios. And thus we anticipate that in higher levels of non-synchronous generation cases for Poland, there would be significant issues related to dynamic voltage control, such as the issues that were identified for the Ireland and Northern Ireland power system, where the levels of RESI we were investigating were up to 70%. So while it's very important to identify the scarcities and issues, it's perhaps just as important, or maybe even more important, to find the solutions. Next slide, please. So the final task in work package 2 seeks to demonstrate system services capability from a range of different resources, and show that this capability can mitigate or at least support the mitigation of some of the significant technical challenges that I've just mentioned. The focus in our final task in work package 2 is on demonstrating capabilities from a range of different technologies and different resources that would be available at times of high renewable generation, in particular resources such as wind and solar generation, demand side management, and batteries, among other things. The same models, methodologies, and scenarios that we deployed in task 2.4 to identify the scarcities are also being employed in this task. However, the models are updated to include new technologies and new capability from existing technologies or new operational policies where needed. So on the next slide, without going into details, I've just described some of the success we've had in demonstrating different mitigations. So the first mitigation is the simulation of the provision of synchronous inertial response, in this case by synchronous condensers. And we've shown that this can help significantly with frequency stability by increasing the level of inertia in the system and reducing the rate of change of frequency. Also on this graph, on the right-hand side, I've shown that the use of non-conventional technologies, in this case, battery technologies, can help to provide fast frequency response to the power system in the case of a frequency disturbance. As I mentioned earlier, including consideration of rock-off or rate change of frequency or inertia considerations in the dispatch could be another possible mitigation, which has also been demonstrated here on the left graph. And finally, on the next slide, the provision of reactive support from non-conventional resources, in this case wind generation, was simulated and illustrated how the voltage stability issues in Poland for both over and under voltage issues can be mitigated. So if you just click forward, please, Christine, you can see how there's a significant decrease in the number of over voltage issues, and essentially all of the under voltage issues have been resolved. Again, these are just a few examples of some of the mitigations that we looked at for a small subset of the scarcities, and all of the details of these mitigation studies will be available in our report, which will be published on our website in the coming weeks. To finish, I'd just like to conclude by summarising the key findings of Work Package 2. So as I mentioned, significant scarcities have been identified in the simulations, not just in Ireland and the Northern Ireland power system, where the levels of RESI were above 70% in our scenarios, but also on the pan-European system, which has RESI levels of around 50 to 60%, as Caroline mentioned. From our analysis, we found that there is no silver bullet when it comes to mitigating the technical challenges. There is not one technology or one solution that we can rely upon. We're going to need a suite of technologies and a suite of different system services capability. Although not discussed here, the challenges can also be financial in nature, which could have repercussions for the future generation portfolio. System services and enhanced market design could be very important mechanisms to support the mitigation of both the technical and financial challenges. And finally, I'd just like to reiterate that a lot of further detail can be found in our reports and webinars, which are available on the EU-SysFlex website. Thank you.
Okay, thank you very much for that, Sheila. It's funny, a question has come in there from Somatios, I hope I'm pronouncing your name correctly. And I think Sheila more or less answered your question. It was just in relation to the capability of RESI to provide services at certain levels. And yes, absolutely it can. And the other thing was that other resources such as batteries and synchronous condensers could also provide such services. And I think that's part of the mitigation analysis which Sheila and the team are identifying and have highlighted here this morning. So I'm going to move on now to grid forming to ensure stability that is presented by Carmen Cardoso. Carmen.
Hi everyone, thank you, Jan. Yes, so I'm Carmen Cardoso. I work with RTE, R&D, and I will present, so next slide please, our demonstrator related to Work Package 3 of the OSMOSE project. So a quick recall on what is grid forming. So there was this project Migrate ended 2 years ago that proposed a theoretical view on grid forming, and basically, if you are not familiar with, is a way of describing the behavior of a converter, VSC converter, as a stiff voltage source. So this entails some capabilities, such as the autonomous creation of a voltage waveform, the capability of landing, and mainly synchronization with other sources. These also have bringing usually the capability to contribute to inertia on short circuit power, but these terms can be confusing when we are talking about converters. So sometimes we prefer to talk about Rohloff limitation, system stress, and separate this from fault current injection. And also lately we are more talking about also these fundamentals voltage short capabilities, so the capability to absorb harmonics and unbalanced current while limiting the interaction, so contributing to some oscillation damping. So in this project, we have many control laws that were proposed and that could behave this way. And there were some relatively large scale simulation that proved that we can have a power system, 100% power electronics working stably. And then we had some laboratory scale experimentation, and we ended up with some recommendation for grid cut. But somehow we were trapped in this discussion of what is the technology really able to do. This can be equivalent to like a synchronous condenser, for instance, to cope with the scarcities that Sheila just presented regarding inertia or voltage regulation. So in OSMOSE, we try to have engaged this discussion with the manufacturer and academy, so we can end this loop of what is the technology capable of doing, and the other question is, what does the system need? So the idea was in this Work Package 3 just to build MVA scale demonstrator to increase the TRL of the technology. And by this, we mean to prove that we can put this control that were proposed in the Migrate project into a commercial hardware, so converter without any need to have a special design of the converter. Then to test the robustness and the effectiveness of the grid forming control in grid connected environments. And at the end, to define these synchronization services and above all, the key performance indicator. So how to measure these services in a technological agnostic way. This is an illustration. So we have all these classical reserves, frequency containment reserve, and now we have also fast frequency response. And what we understand by synchronous services, everything that is below. So that's going to be bring back this grid forming capability. So if you know with grid following is current controlled classical converters, so we say that they can provide a fast frequency response, or maybe not synchronization services. So the idea is we know that this conceptually at the moment, and we try to define this and also provide an insight in how one device can provide these multi-services. And also we have this equivalent view in voltage regulation. So at some point we have fast voltage, dynamic voltage regulation. And at some point there is what we call system strength, is the equivalent of the synchronization service for voltage stability. So next slide, please. So to achieve this goal, so what we did is that we conceived 2 demonstrators on grid forming, but also on these synchronization services in battery energy storage systems. So we have one built ad hoc for the demonstrator that was more focused, as I said, in the technical feasibility of putting this migrate control into conventional hardware. And for this, we use like more a hybrid energy storage system. This is, we combine ultra caps with the battery. So I know the image is a bit small, but the idea in the small square is below. You have in the left-hand side batteries, and then you have 2 groups of ultra caps. So then you have 3 DC-DC converters that interface the DC bus with the different energy sources. And then you have the AC-DC converter, and here is where we put the grid forming control. So after a phase of AMT design, we have AMT simulation and control design. So the converter was built by Inge team, our partner, Spanish partner, and we performed power hardware in the loop test in this demonstrator. So in the picture, you see 5 cabinets. This is the full converter with the DC-DC converters, the AC DC grid forming converter, the filters, DC side, everything. It's the real power device. And in the right-hand side, you see in black 2 racks of something, but this is ultra caps. So we put it behind the DC bus real ultra caps racks and battery racks. So we test the system at reduced power because of the grid emulator that we use. We could not test at 1 MVA, so we tested about 100 kVA. And the grid emulator could perform many things like phase jump, unbalanced fault, inject harmonics, and anything that we wanted. And there is another demonstrator that is at EPFL campus. So they had this battery already in service. And first of all, they work in RTDS. So they did real-time simulation to check if we could differentiate in a grid the performance of a grid following and a grid forming battery, only knowing the measurement without knowing the control load. And then they perform some on-site test with this battery in the EPFL grid. And for the detail on the testing, I invite you to check tomorrow webinar. Next slide, please. So here I just want to summarize the key innovations and messages of the work package without getting into the details, but directing you to forward reading. So I would say that the first key message is that first objective, we prove the technical feasibility of grid forming and to the provision of these synchronization services with off-the-shelf VSC in a battery energy storage system. And there are already 2 published deliverables. One is they are already online, so the overall specification of the demonstrator and the multi-service control algorithm proposed by EPFL. And we also have the result of the factory acceptance tests on the grid forming demonstrator that are already published. And as I said, we could demonstrate robustness to a large number of faults, unbalanced fault, and in harmonic distortion. Permanent unbalance also, we could check the response. So here is a quick image where you see that you have this voltage source behavior and you absorb harmonic current. And then we have also a great work performed at EPFL on this definition of key performance indicator. So as Chela was saying, the problem is of this inertia scarcity is rock off. We could differentiate only by PMU measurements the fact that when you have really fast frequency response with a grid following, or when you have grid forming behavior, you see in equivalent tests, this is a real-time simulation, a quite difference in the shape of the rock-off. So I invite you to check this paper that the idea was to discriminate a grid forming from a grid following from measurement from the service provided to the grid. So we could prove that we can measure this effectiveness of the service provided by the grid forming capability.
Carmen, I'm just conscious of time, but we need to start finishing up.
Yes, please, so we can go next. And the only thing that I need to add is here is that when you go to an existing facility, there is a important concern in the capability. So they have this real-time control to respect the capability of the converter. Finally, my last slide, I would say that so we need to keep breaking the barriers that prevent any technology having grid forming capability to provide synchronization services. And this requirement needs to be well-defined. If they are too tight, we can leave some technologies out or entail over cost. Too loose, we may lack of incentive and have low quality services that will at the end lead to high prescriptions. And technical questions that we see as open, we are looking into now how to do this like with HVDC. We see that research is going on this direction. Of course, there are concerns in minimal energy buffer and current capability. People is working on this. And also, if we have this deployed with different manufacturers, with different controls, there are concerns about interaction. So we need to study this. TSO, we have the homework of trying to define this system-wide local needs for synchronization services. Now we are starting to get proper models to do this. And we are now working on how to put this into grid code and standards, how to define connection requirements and compliance verification procedures, and the suitable certification for this synchronization service.
Okay, thank you very much, Carmen. I'm going to move on swiftly because we're running out of time. We want to present on the demonstration project. So I'm going to hand over very quickly to Miguel Marquez of EDP, who's leading the demonstration project on the virtual power plants for EU-SysFlex. Miguel.
Thank you. Thanks, John. Hi, everybody. So yeah, my name is Miguel Marquez. I work for EDP, and my my task for the next 10 minutes is to squeeze in 3 different demonstrators, 3 different virtual power plant demonstrators, and that I'll focus on. So on the next slide. So my objective is really to present them, to show you, the differences, the complementarities between them, hopefully show their objectives, the current status, early results, and the next steps. So the next one, key messages here, and I'll jump right into them. If you're not familiar with the concept of a virtual power plant, I think we can pack it in under the VPP/aggregation concept. So the idea here is to jointly operate, control different assets of different natures. Within the EU-SysFlex, there's 3 different demonstrators, one in VPP/aggregation demonstrations, one in Portugal, another one in France, another one in Finland. I myself am working in the Portuguese work package leader for the Portuguese VPP demo. But I'll try not to give too much detail on the Portuguese one and neglect the other 2. In general terms, the moment we're in right now is that we're starting to test or have already tested quite a few of these concepts. And this comes in after an extensive time of preparation, development, and early testing. And now the demos are starting to actually yield some results. Some of them are already, we already have a bit more solid results. Some of them are midway through their demonstration stage. We do feel that this VPP/aggregation concepts are interesting for the future. So this can be an interesting way to provide flexibility services, either the already existent VPP flexibility service or the future flexibility services to the VPP, or the aggregated operation of different assets can be a solution for the future power systems, and are well in line with the objectives of project EU-SysFlex. So let me jump right into the 3 demos themselves. So one in Finland focusing on the distribution energy resources, so more on the aggregation, more of an aggregation testing. Another one on France on the renewable and storage VPP. And a final one, which is the one, as I said, I'm leading, which is utility scale hydro and wind VPP. I should say here, so for the Portuguese VPP demo, it's EDP together with a number of partners that are currently working with us. For France, the demo leader is EDF, and for Finland, the demo leader is Helen. And so I'm here on their behalf presenting the three demos. So for the Portuguese demo, we have a large hydro plant combined with 2 wind farms, and the idea is to test the operation of this VPP, doing not only a joint bidding, but also the joint operation of this, using the VPP as a way of integrating larger shares of renewables, again, in line with EU-SysFlex objectives, and also show that this could be an interesting way to manage a portfolio of different assets. So testing the VPP as a tool for a market operator. For the French VPP demo, there's a large battery energy storage system together with residential PV panels, which are actually emulating utility scale PV panels, so multi-megawatt scale, together with the wind farm. So we're looking at storage plus renewables setting. And the idea is to provide multi-services from multi-resources, so which you will see in a second. For the finished VPP demo, we're looking at low voltage mostly, so using different types of batteries at an industrial scale, at an office scale, at the residential scale, so at a lower scale as compared to the Portuguese and French examples. And then there's also EV chargers used as flexible loads, and also a PV plant installed in a building in Helsinki. The idea here is to test integration of these small distribution assets, and the idea and the objective really is to input all this into an aggregation platform and use this not only to provide flexibility services in the form of active power for frequency control, but also in the form of reactive power for things like like adjusting the voltage level in the connection point between the DSO and the TSO, which you will see ahead, but I'm already trying to accelerate. So in the next slide, you'll see the different status of the three. I mentioned it briefly in the beginning. For the Portuguese demo, we did the first test, which was very successful. We are also planning to have additional tests in the future, but at least this first milestone is now achieved. The testing of the whole VPP, of the French VPP, is undergoing as we speak. So our colleagues from EDF, together with other consortium partners, are now carrying out this testing. For the finished demo, the demonstration stage is now completed. So it's now down to reporting the results and yielding the first conclusions and KPIs for the finished demo. Next, we have the first results. So as I said, we're midway through the presentation, to the demonstration, but we already have some interesting results for the Portuguese VPP demo. We are now able to compute accurate and reliable dispatch schedules and bid suggestions for this VPP, which again is comprised of a large hydro, very flexible hydro, and wind. So we were able to use it as a one single unit and compute dispatch schedules and bid suggestions for this. And we were able to do, and we did that, we tested it in real time, do the deviation handling. So adjusting the hydro plant to the fluctuations of the wind farm production. For the French demo, as I said, well, the testing is now taking place. So the results that we have are simulated as we speak, but we have already understood that, and our colleagues from the French demo have understood that it is indeed possible to provide different services at the same, simultaneously provide different services using the assets within the VPP, which again, wind, PV, and storage units. These are some of the results. Not easy to read, but I mean, there's a lot of more detail available, and this goes for all the other demos. A lot more detail available in EU-SysFlex website in our deliverable section, document section. For the Finnish VPP demo, again, wrapped up and now reporting results. It is easy to understand that for now it is possible to have distribution assets connected to low voltage and medium voltage grid, providing services to the TSO. So providing services to the TSO to help support the market. And we have different, as I said, not only frequency control, but also reactive power in TSO-DSO connection points. Finally, and I'll wrap it up in 1 minute. In the next slide, the next slide we have some next steps of the demos. So for the Portuguese demo, we are assigned to report and assess the results. We also want to test the hydro plant in pump mode, which is something we have not tested yet. We did it in turbine mode. But if market conditions exist, we also wanted to test this with the hydro plant in pump mode. This is a reversible hydro plant. And then, define and quantify the benefits of the concepts versus business as usual. For the French demo, the idea is to finalize the VPP demonstration, which, as I said, is taking place as we speak, and then assess results. Now, beyond EU-SysFlex and key things that we want to test in the future and that we believe that can be beneficial for the system. So the very obvious next step is to replicate this in different scenarios, in different technical and regulatory scenarios. We're doing this in 3 different countries, but we should be able to do this at a European scale, using larger sized units, a larger number of units, of battery storage units, of wind farms, so that we prove that this is a scalable concept, which is obviously very important for us to test. Two final points. One is that there's still control and forecast algorithms to be improved. There's a lot of things that could change. One example is having faster response in the EV charging control for the case of a Finnish demo. And finally, last but not least, there are indeed regulatory barriers. This goes for not only Portugal, but also the other demos. In Portugal, I'm most acquainted with. Some regulation as of today does not allow us to do some of the things we're doing here. So, multi-resources providing multi-services. But once the technical benefits are there, I'm sure that the regulatory barriers will start to come down. And I think, but these changes do take time. And our goal now is to demonstrate technical viability, but also for the longer future, the beneficial impact of this, again, at the European level, not only technical, but also, financially.
Great, thank you very much, Miguel. We are running out of time, so I'm going to hand over very quickly to Alessio. Alessio, if you can get this over and done with as quickly as possible, and then we might have a couple.
Yeah, I'll try to be in the 10 minutes.
yeah. Go ahead.
Okay. Good morning, everyone. I'm Alessio Siviero, and I work in Terna, the Italian TSO, in the innovation factory, the system operator. So the question we were trying to ask ourselves when we started working on the OSMOSE project, at least in the work package number 5, and the specific task regarding renewable energy plants, is is there a way we can use these resources to provide those ancillary services, both regarding voltage regulation and frequency regulations that were usually provided by traditional power plants. Are RES plants capable of providing such services? So was the main question. And we were asking then ourselves, what would the requirements be for such RES plants so that they could provide a quality service that could be comparable to those provided before by conventional plants. So as far as voltage regulation is concerned, what we basically we want to ask to these plants is to be capable of varying their reactive power provision according either to a Q set point or to reference voltage set point for what is called a centralized or local regulation. As far as inertia is concerned, we all know that the dismissal of conventional power plants is posing a problem, a threat to grid inertia. So we've also thought of trying a new service based on a power response which is proportional to the frequency derivative. Next slide, please. So the plants, so what we see here is just regarding these two plants, Vaio and Pietragalla. Vaio by Edison, EU Energy Speciali, Pietragalla run by Enel Green Power. So it's just a small part of the whole OSMOSE task 5. So this part, I'm just describing the part regarding RES. There's also a whole new world regarding DSR, DTR, and congestion management by innovative means. With these two power plants, Vaio is a wind power plant, 35 megawatt total. Pietragalla is an integrated wind and storage power plant. We want, with these two plants, as I was saying, we want to technically assess the capability of wind plants and an integrated system, wind and BESS system, to provide both AVC and technically characterize the synthetic inertia provision by wind turbine and by a BESS system, so battery energy storage system. Next slide, please. So as far as we could see with the implementation of synthetic inertia, we will see that the implementation, the development, implementation of such service was more challenging, and we could say that some more R&D is needed on the topic. The two implementations we build on in Pietragalla and Vaio. I say we, but big part was, of course, brought over by Enel and EDWE, is that we have in Pietragalla, basically there is a system which is called here SICD, Synthetic Inertia Control Device, which actually measures the rock-off. The measurement is filtered, and then it is used to compute a power point, which is then sent directly to the BESS system inverter. So the main challenge here was to measure the measurement module of the CICD, and starting, of course, from the very high frequency, very high sampling frequency measurements. And now the tests are basically about to start. The implementations are done. In the Vaio system, as I was saying before, the contribution will be given by the turbine itself. So trying to use the kinetic energy stored in the rotating mass. So there were some modifications to be done in the converter firmware and in the PLC software. And these logics were never tested before by Siemens Gamesa on this type of turbine. So there are tests at the moment going on in the bench test going on right now in Vaio, and the implementation is therefore coming in the following week once these tests are over. Next slide, please. As far as AVC is concerned, we can say that the implementations were just followed a similar path, since in this case we had to operate some EDWE and Enel had to operate some modifications on their local control systems, basically. And indeed, there were the need to, at this moment, the TSO does not control such plants. So there was the need to define an appropriate list of signals and commands and set points and measurements that would guarantee a proper provision of the service. So the challenge was, one of the challenges was that, for example, in Pietragalla, there is the need to coordinate the storage and wind plant action, while and so this will also somehow be tested during the experimentation, the demonstration part. While in Vaio, there is the possibility to test, there will be eventually the possibility to test both a direct and indirect communication with the TSO for the provision of the service. And this will allow to test especially how the rapidity in the provision of the service will change. So for this part, for the adequacy demonstration, it has already started in the value plant. And if we go to the next slide, I can show you a little bit of what these tests are about. We're talking about static and dynamic regulation, basically. So for the static, we want to the set point is variated slowly. So we want to assess if the plant is capable of actually reaching that set point with a certain precision, while dynamic regulation is more of a stepwise change in reactive power, and then followingly also we will test the V set point, the tension set point reaction, and see how dynamically the power plant will respond. So if we go to the next slide, we can. You were saying something, John.
No, go ahead. Finish up, Alessio. We're near the end here. So
yeah. It's done. Okay. So the key messages is that, as I was saying before, with this implementation, we want to test some new services provided by new resources, and by new resources I mean resources that were never allowed before to provide such services. So the implementations are almost done. We believe that some more effort is needed, probably on the synthetic inertia, especially, and the testing will. However, the testing will provide some more insights on what are the eventual remaining bottlenecks. And if you go to the final slide, I can tell you that in the next weeks, we will go on with the test. Actually, in Vaio, they've already started, speaking of ABC. In Pietragala, they will go followingly. We go first locally, and then with a remote test with set points sent by the TSO, while synthetic inertia experimentation is going to start afterwards. In Pietragala, things are basically ready. With Vaio, we will need a little more time for the end of the tests I was describing before. Thank you very much.
Thank you very much, Alessio. Unfortunately, we've run out of time for our Q&A session. We do have a list of questions that people have posted on the Q&A to slide there. So if anybody else wants to ask any questions, we'll try and leave it open for a little longer. Post them now while you can. I have found it fascinating to have these two projects that are very important strategic projects for Europe. Very complementary, I think that's my conclusion. And there's lots of challenges which both projects are attempting to address with respect to system operation. So look, I'd just like to thank everybody for attending. I'd especially like to thank all of the speakers this morning who put in a lot of time and effort into developing their material for today. As I said, we have 2 further sessions this week. So please do join us for those sessions. Thank you very much. And I think we can leave it at that. Say goodbye. Thank you. There's all our contact details as well. So if anybody wants to contact anyone, please do, and we will respond to those questions that have been posted. Thank you. Bye now.